Hello everyone, my name is Swami Venkatesan. I'm a Senior Solutions Architect at Cadence Design Systems. In today's presentation, we will discuss strategies and methods of using the portable test and stimulus language, high-level modeling techniques to augment UVM verification. We will look at some typical verification challenges faced when doing UVM-based verification and see how PSS can help solve these problems. Let's start with verifying a deep state machine. Consider the following USB link training and status state machine that has 12 states, including 4 operational states, U0, U1, U2, and U3. A typical test scenario requires transition to one of these operational states, say U1, before sending traffic. This transition can happen in many possible ways as shown here. Testing this deep state model in system Verilog is hard to do as they require creating controlled stimulus patterns that allow transition through many hops and potentially many parts to reach a target state. Writing UVM sequences for these FSM state traversals require complex constraints between commands, arrays, and often heavy procedural code that takes care of state dependencies and careful scheduling of the state traversal, all of which is usually done manually. With PSS, you can use the semantics of state objects to model this state machine and allow the PSS tool to solve the dependencies between the state transitions. This automation can result in exhaustive state traversals. The state objects ensure that a strict sequential scheduling between the producer and the consumer action is enforced. The state dependency of transitions to state, let's say U0, and transition to state U1 can be modeled as shown here. Based on the matching constraints between the actions and the state objects that they exchange, the PSS tool would infer dependent actions and complete the dependency chain for creating a legal concrete solution. The users can create many such concrete solutions with different seeds and then map it to their system Verilog elements to create multiple system Verilog test cases. In this way, they can create exhaustive state traversals. Another challenge in UVM is that the reuse of virtual sequences developed from different teams cannot be used at high levels of verification. Consider the following case of two teams verifying their subsystems independently. The Ethernet subsystem team is verifying their Ethernet subsystem data path. That includes initialization of the Ethernet IP, programming the DMA buffer descriptors, and initializing the DDR controller. Once all this is done, they can send up a traffic to send Ethernet. A team testing the PCI Express subsystem does a similar data path testing that includes setting up the DDR memory controllers, followed by setting up the buffer descriptors in DMA, and eventually invoking the PCI Express agent to send the traffic. At a chip level, the teams are often tasked in data path testing of the Ethernet to DDR memory space, and also the PCI Express to DDR memory space in concurrently. One logical place is to start reusing the virtual sequences that have been previously developed and tested at subsystem level. However, such virtual sequences developed are often unusable due to resource collisions and multiple random initializations that they may have. PSS solves such resource constraints and collisions upfront by capturing the dependencies in the individual actions and thus allowing users to mix and match PSS scenarios from multiple IPs and subsystem teams. A PSS tool would typically solve the entire scenario, taking into consideration the resource dependency and the scheduling needs of the scenario, and will ensure that only a legal scenario is always created. So in this case, looking at the previous problem, the PCI Express scenario developed by the PCI Express team will have the dependency modeled. In this case, the PCI IO sequence has a dependency model to ensure that the PCI Express initialization sequence and the DDR initialization sequence are complete. The DMA transfer operation also has an input dependency to ensure that the DMA data buffers are available before the transfer can happen from source to destination. Similarly, the Ethernet scenario developed by the Ethernet subsystem team have their dependencies modeled accordingly. Now, when you go to chip level, you can reuse scenarios coming from the subsystem teams, namely the PCI Express and the Ethernet teams, and create your high-level scenario. A PSS tool will resolve all the dependent actions. It'll make sure that the synchronizations are enforced and ensure proper ordering of the operations. In this case, it ensures that the downstream DMA transfers, Ethernet transfers, and PCI Express transfers can start only after all the upstream initialization actions. For example, the DDR initialization, PCI Express initialization, and Ethernet initializations are complete. This way, the PSS tool always creates a correct by construction solution with no resource collision and all the memory segments properly resolved. SV has excellent declarative constraint language support. However, for modeling scenarios as subsystems and beyond, the low-level constraint model in system Verilog is often hard to implement and debug. A good example can be seen in a multimedia subsystem verification that has multiple input engines and output engines. There are rules on how the input and output engines need to be mapped. In this case, there are 5 input engines and 3 output engines. You have use cases which clearly say you can only at any time operate a single output engine or a single output engine mapped to one input engine or a single output engine mapped to 2 input engines at most. Also, the concurrent operations should not use the same engine instance. While modeling in system Verilog, you can use the system Verilog constraints for constraining the mapping scheme, usually a flat representation. And you can easily see this is hard to reason and debug for a relatively simple problem of resources. With PSS, we can capture this intent at a higher level and state it in the terms of the problem, which is easy to reason, easy to debug, and you can capture it abstract scenarios to create higher level behaviors. So if we look back at the previous problem, we can use resource objects in PSS to capture the resource availability of input engines and output engines, and then create operations which put a claim on the resource. For example, a B operation claims a single instance of B engine. A AB op1 claims a resource of single A engine and single B engine. And AB op operation claims 2 A engines and 1 B engine. This model is easy to reason and debug. Now you can create more abstract scenarios for your behavior. In this case, we are processing multiple phases of images. In each phase, we select one or more of the available. A PSS tool will solve the scenario, create a UML activity diagram or some sort of a scenario from which you can create your system Verilog code for your test. The other verification challenge in UVM is vertical reuse. Once you have a programming sequence in UVM, you cannot reuse at SOC level. But consider a case where a subsystem environment is creating programming sequences in their bus-based UVC. Now, when you go to SOC level, this programming sequence usually needs to be run on a CPU, and the UVM bus-based sequence cannot be reused here. PSS 2.0 introduces hardware-software interface, which captures register models, memory availability, and also threads and synchronization concepts, with which you can map your behavioral model into low-level register data structs, populate those register structs with the PSS attributes, and map it to a low-level implementation of register programming sequence, like writes and reads to your target interface. These writes and reads can happen in system Verilog, where you call the system Verilog task, where you map the writes and reads to system Verilog tasks, or you can map it directly into embedded C as pointed dereferences. The last challenge is about redundant coverage. UVM is excellent in randomization. However, there's no correlation between the items. So what this means is, in order to create a coverage of a 30 bins cross coverage, you create more items where some items are redundant. With PSS, it's much more optimal since PSS does the solving upfront in many cases. For most of the input attributes, you can do the upfront coverage generation. And using PSS tool directives, you can create optimal test scenarios needed to get to 100% coverage. In this case, for 30 cross bins, you just create 30 operations to get 100% coverage. Okay, thank you for listening. I hope this session was useful. Thank you very much.